let's do chapter 14, problems 6, 7, and 8. So problem 6 first, and this is on page 388. So a reading of the problem: calculate the average density of a red giant star in grams per cubic centimeter. Take the star's mass to be 2 times 10 to the 33rd grams, and its radius to be 3 times 10 to the 12th centimeters. So this is about the same size as our sun as far as the mass goes. Our sun is 2 times 10 to the 30th kilograms, and this is 2 times 10 to the 30th kilograms as well. So it's exactly the mass of our sun. But when it goes into the red giant phase, the outer layers are very, very thin. And we're going to find out just how thin right now. And the radius to be 3 times 10 to the 12th centimeters. How does this density compare that with the air we breathe? And the density of the air we breathe is 10 to the minus 3 grams per cubic centimeter. You may recall that the density of water is 1 gram per cubic centimeter. So our air on this Earth is 1,000th the density of water. So let's remember that density is equal to mass over volume. And the mass is given to us as 2 times 10 to the 11th grams. And we're going to use the units that were given, grams. And we have to divide that by the volume. Now the volume is always equal to 4/3 times pi times r cubed. So it's equal to 4 over 3 times 3.14. And the radius is given to us as 3 times 10 to the 12th centimeters. And we're going to use the units that were given as well. So first thing that we're going to do is cancel 3 and 3.14 in this level of estimation. So what we're left with is 4 times 3 cubed times 10 to the 12th cubed. So this is equal to 4 times 27, which is 3 cubed, times 10 to the 36. Because a to the n to the m power equals a to the n dot m. So 10 to the 12th to the cube power is equal to 10 to the 12 dot 3. It equals 10 to the 36. Now 4 times 27 is just about 100, which is 10 squared, times 10 to the 36. So this is equal to 10 to the 38 as the volume, and it's cubic centimeters. So if we go back to our problem, we see that we now have the volume, and the density was equal to 2 times 10 to the 11th on top, and our new volume on the bottom. So the density continues to be equal to 2 times 10 to the 11th on top, and 10 to the 38 on the bottom. So let's give this as a 2, and now 10 to the 11th over 10 to the 38 is equal to 10 to the 11 minus 38 equals 10 to the minus 27. So it's equal to 2 to the 10 to the minus 27 grams per cubic centimeter. Now we're going to compare that with the air we breathe. So the red giant to our air is 10 to the minus 27th, dropping the 2 for a moment. And we are given that the air we breathe have a density of 10 to the minus 3. So this is going to give a net that it is 10 to the minus 24 times thinner than the air that we breathe. That's a decimal point, 23 zeros, and a 1 is how much thinner the red giant atmosphere is than the air we breathe. So it's enormously, enormously thinner. The fact that it glows so much and puts out so much energy is merely due to its exceedingly gigantic size. So the next problem we're going to address is problem number 7. So we're on page 388 again, problem 7. So a reading of the problem: how long will it take a planetary nebula shell moving at 20 kilometers a second to expand to a radius of 1/4 of a light year. Well, time is equal to the distance that you go divided by the speed you go. As again, you well know, if you drive a distance of 120 miles at a speed of 30 miles in 1 hour, then the time for your trip is going to be the distance over the speed, 120 over 30, or 4 hours. So in this case, we're giving that the distance is 1/4 of a light year. So we recall that 1 light year is equal to 10 to the 16th meters. So the distance is 1/4 of that, 0.25 times 10 to the 16th. And we are traveling at the speed of light, which is our usual 3.0 times 10 to the 8 meters a second. And we want to find out how much time this is. So, oops, slight difference there. We're given that this is expanding at 20 kilometers a second. So it's not light, it's the expanding density that we're tracking. So it's expanding at 20 kilometers a second. So it's expanding at 20 kilometers a second, which means 20 times 10 to the third meters a second. So let's make a slight change in the denominator. Make that to be 0.20 times 10 to the fifth, because we moved the decimal point 2 places to the right. And the motivation for doing that is that these two decimals will now cancel, and we get 10 to the 16th over 10 to the fifth. Come on, whiteboard. Awaken. Well, we just lost the whiteboard for some strange reason. Completely. Oh, there it is. Let's see if it's back. 10 to the 16th over 10 to the 5th. And that's going to be equal to 10 to the 11th seconds. So if we want to ask the question, how many years is that? Then we have 10 to the 11th seconds, and we divide by the number of seconds in a year, which we now know is 3.2 times 10 to the 7th. So we're going to change this to 10 times 10 to the 10th seconds, which is another way to write 10 to the 11th, over 3.2 times 10 to the 7th. And 3 goes into 10 3 times, so this is 3 times 10, 10 to the 7th minus 10 minus 3 is 10 cubed, so it's equal to 3,000 years. Okay, so we get our answer. Now the last problem is problem number 8. And go to a new page, page 388, problem number 8. Now remember, when you answer these questions on the quiz 5, you must put in the steps. You can't just memorize the answers and write down bare answers. We need to see the steps and the work. So problem number 8, calculate the Doppler shift of X-rays emitted from shocked silicon in a supernova remnant if the ejected material is moving at about 5,000 kilometers a second and the X-ray line is at 0.66 nanometers. We should be very grateful that silicon is ejected from supernovas, because that is the major element in our Earth. We are mostly silicon. So let's write down the formula for the Doppler shift. The velocity of the object divided by the speed of light is the wavelength shift of the object divided by the base wavelength. And we're told that the speed of the object is 5,000 kilometers a second. So that's 5,000 times 10 to the third meters a second. And the speed of light is 3 times 10 to the 8th meters a second. Now delta lambda is what you're looking for. It's the answer to the problem. And we're given that the laboratory wavelength of the X-ray line is at 0.688 nanometers. 0.688 times 10 to the minus 9 meters. Because a nanometer is 10 to the minus 9 meters. So let's continue with our calculation. We have 5,000 times 10 to the cubed. Now, if you multiply both sides of the equation by 0.688 times 10 to the 9th and 0.688 times 10 to the 9th, then they cancel on this side and they remain on the left side. So it's times 0.688 times 10 to the minus 9. And we'll put in those minus signs. That was a verbal typo. And on the bottom is 3 times 10 to the 8th, and this will be the answer to the problem that we're looking for, the wavelength shift. So let's make that a little bit cleaner. Instead of 5,000 times 10 to the cube, let's write that as 5 times 10 to the 6. And then it's going to be 0.688 times 10 to the 9. And on the bottom, we're just going to leave it as 3 times 10 to the 8th. And that's the answer to the problem. Now let's just rearrange the numbers. 5 times 0.68 times 10 to the 6 times 10 to the 9th over 3 times 10 to the 8th is the answer to the problem. And 5 times 0.6 is about 3. 10 to the 6 times 10 to the 9th is 10 to the 15th over 3 times 10 to the 8th, which was our motivation for moving things around. So 3 goes, and we have 10 to the 15th over 10 to the 8th as the, oops, it's a minus 9. I keep forgetting that. That's a minus 9. So we have on the top, we have plus 6 and a minus 9 for a net of minus 3. So we have a 10 to the minus 3 over minus 8. 10 to the minus 3 over 10 to the 8th, and that is going to be 10 to the minus 11th. The reason being that a to the n over a to the m equals a to the n minus m. So 10 to the minus 3 over 10 to the 8 equals 10 to the minus 3 minus 8 is 10 to the minus 11. So this is our answer, 10 to the minus 11th, and the answer is equal to the wavelength shift in meters. Now, if you want to know that in centimeters, which is popular, there are 100 centimeters in a meter, so it becomes 10 to the minus 9th centimeters. And if you want to know that in nanometers, then you have to divide that by 10 to the minus 11. You have to divide by 10 to the minus 9, because there are 10 to the minus 9 nanometers in a meter. So this is equal to 10 to the minus 2 nanometers.